right from the beginning, if I just remind you, and the videos are all there right from the beginning of this lesson or this topic, chemicals of life. We talked about water, then inorganic nutrients, and then from inorganic nutrients, then we talked about organic nutrients, and we began with carbohydrates. And with carbohydrates, we saw that they can be classified into monosaccharides, disaccharides, and polysaccharides. And we saw monosaccharides and the different examples, okay, where they can be triose sugars, pentose sugars, and hexose sugars. We saw all that, and we gave the different examples of triose sugars. We gave the different examples of pentose sugars and how you can clearly tell which one is a pentose sugar and which one is a triose sugar. Then we gave examples of hexose sugars, and how you can clearly tell that this is glucose, this is galactose, this is fructose, and stuffs like that. So we introduced disaccharides, where we talked about something simple, the formation, okay, how they are formed from monosaccharides by condensation reaction, and the two are joined together by a 1,4, okay, glycosidic, and I showed you why it's 1,4, okay. It is condensation between carbon 1 and carbon 4, and we gave some examples where we saw maltose, and we say that it is formed by condensation of two glucose molecules, and we saw that is common in germinating seeds. Then we gave sucrose, where we were able to discover that actually this is the sugar that we take, and we take this every day, every morning, every lunchtime, and every supper. Some of us who take tea like nothing. So you take this sucrose frequently, and we were able to discover that it is made up of glucose and fructose. Then we saw lactose, and we were able to discover that this is milk sugar, okay, milk sugar, and it is formed from condensation of a glucose molecule and a galactose molecule. So that's basically where we stopped from. So let's see how. Did we talk about how they condense? I think no. That should be in our next slide. Yeah, we talked about the properties. Yes, I remember. And I told you that whenever you are to talk about properties, just think about the sugar that you like. When you were young, we used to steal sugar. Okay? So think about that childhood game. You steal sugar and you start licking. Then when mommy comes and be like, Emma, did you steal sugar? And then you be like, no. But obviously you cannot say no. Crystals will just be on your cheeks. So just think about that game. Whenever they say properties, where number 1, was the sugar sweet? Yes, it was. Was it crystalline? Yes, it was. The crystals remain on the cheeks. Otherwise, if it's a powder, then you can just and you rub it. Was it soluble? Yes, it was. That's why whenever you would put it in your mouth, it would dissolve with ease. Then now these ones, they are kind of technical. Now, all monosaccharides, they are non-reducing sugars. Non-reducing sugars, except now people, we are now beginning to complain, except maltose. So the rest are non-reducing sugars. they do not reduce Benedictine solution. They do not reduce copper 2 ions in Benedictine solution to copper 1. So
Excuse me,
therefore,
sir.
yes, Edwin,
Why maltose?
for it, maltose it can reduce. And why maltose? Why did you ask? You can go ahead and ask so that I can get to know how to answer your question. What are you interested in?
Why is maltose reducing sugar?
Okay, why is maltose reducing sugar? That's good. Now, this one, the maltose is formed from aldose sugars. So it has an aldehyde groups. It has aldehyde groups. But for these ones, for instance, fructose, it is a ketose sugar. So it has that keto group. Some books they describe it as a hemiceto group. Whereas this one, it has an aldose group, the maltose, because it is formed from 2 glucose molecules. So this aldose group, it is the one which can be oxidized into a carboxylic acid, and then for it, the Benedictine solution, the copper, becomes reduced to copper 1. But for these ones with this hemiceto group, with this keto group, now it cannot be oxidized. Hence making these two, the lactose and the sucrose, to be non-reducing sugars, whereas maltose to be a reducing sugar. I hope that one is okay. Now, don't ask me that what is, now that will be too much of you. Okay? And according to our syllabus, no one is going to ask you that. Then they can be broken into simple sugars using the action of mineral acids and enzymes. Okay? Yes. So let's actually see the formation of these disaccharides. Yeah, I actually remember I also talked about this. So the disaccharides, for example, this is glucose and glucose, so this is maltose. So it is going to be formed by a condensation reaction. And the condensation reaction is that reaction that involves loss of a molecule. And in this case, you are losing a water molecule. So where this is carbon 1, 2, 3, 4, 5, and 6, then this is carbon 1, 2, 3, 4, 5, and 6. So when these carbon 4 and carbon 1, the OH groups on carbon 2 and carbon 1 and carbon 4 approach each other, they will undergo what we call a condensation reaction, where they form a water molecule, and a 1,4 glycosidic bond is going to be formed that will hold these two molecules together. Now further condensation of each, it will lead to what? To formation of a complex carbohydrate, which is starch in this case. Similarly with fructose, when we are forming fructose, the glucose molecule is going to condense with, when you are forming sucrose, I think that's what I said, the glucose molecule is going to condense with the fructose molecule, okay, and what is formed is sucrose, okay, and then a 1,4 glycosidic bond is going to link the two molecules together, okay, forming the sucrose. So likewise, with lactose, same thing. The glucose is going to condense with galactose. And what is formed is lactose. Okay? Yes. So chemical test for disaccharides, reducing sugars, if it's maltose, then we shall use a Benedictine solution.
Teacher, will it require for us like to write those equations like that?
Yeah, in some questions they can say.
But then you have not told us how to draw it. You have not told us how to locate those. The what? How do they call them? I've seen the hydrogens. The what? You have not told us how necessary to locate them.
Okay, that's good. That's a good concern. That's a good concern. Let's go back. So, yeah, so that was really a good concern. So, let's say for maltose, okay, it is formed from condensation of two glucose molecules. So you're going to draw your glucose, where this is the O, and this is the carbon, and then this is the carbon, and then carbon, and then carbon, and then carbon here. So this is an alcohol, CH2OH. So on carbon 1, you have there the OH.
Teacher.
Yes,
Why are you drawing six-sided? Why are you drawing us with six-sided?
because that is the structure of
For
group.
it has six
Yeah, it has
carbon
six.
atoms.
Yeah, it has six carbon atoms. But one obviously it's oxygen. Then the other one, the sixth, it's like a branch on the overall ring. Does it make sense now?
Like you have said that it has six carbons, but
Yes.
again you are saying that of course one it is oxygen and another an alcohol.
Okay. So this is the ring structure of glucose, and this is how it is. In a previous lesson, I showed you how it rings. Okay. So the oxygen is going to donate the electrons to this carbon, okay, to form this, and then this is going to be our carbon 1, and this is our carbon 2, carbon 3, carbon 4,
Why are you starting from where
carbon 5.
ends?
So why am I starting from where oxygen is? Now I'll take you to organic chemistry,
Hey,
whereby that carbon atom with a functional group becomes carbon 1.
I remember.
You remember that? That's good. That's brilliant.
Then why are you giving in the glucose segundo? Why did you add that alcohol? That CH2OH. Why did you add it there?
Now when it rings, when the process of ringing, the sixth carbon atom remains outside, like a group that is attached on the overall ring.
But you have put it on the fifth. Yeah.
That's where it is.
Hey.
Uh-huh. Is it okay now?
I'm seeing the hydrogen and a hydroxide on some carbon.
On this carbon here?
Hmm.
Yes, there are others, but I didn't show them because in this reaction they won't participate. But the structure, you would have the H here, and then the OH here, and then you have the H here, and then the OH here, okay, and then the OH here, and then the H, okay, and the H. Does it make sense now? So that is the overall structure of glucose.
So the oxygen does not have the H and the OH. For it, it's like that.
Oxygen is oxygen. Remember, oxygen forms a maximum of two covalent bonds. So it has formed one here and another one here. So that's all. But for carbon, The other concept of organic chemistry, carbon cannot go above 4 bonds, and also carbon cannot go below 4 bonds. So that's why you have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Does it make sense now?
Yes,
It does, eh?
but still confused.
No, it's okay. You speak.
I'm asking myself how
Mm.
that CH
This one, eh?
came. Yeah,
This one, eh?
yeah.
Maybe let me take you back to the ring structure, to how the ringing comes about. Where? Not here. Yeah, here. This slide. You remember this slide in our previous lesson?
Yes.
So this is sorry. So this is the straight chain. This is the glucose in straight chain in linear form. Okay? So because this carbon, it's the one with a functional group. Which functional group? This CO, this CHO. This is an aldehyde. In organic chemistry, now this is a functional group, and it is preferred to the OH group. Now we are talking about something of organic chemistry. You remember the other order of preference. So that carbon therefore is considered to be carbon 1. Okay? And so this is carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. So that's why you were asking that why carbon 1, why this is carbon 1. Because it is the one with a group. Now, is it okay? Is it still okay, or
You have not answered me.
I'm going to answer. I'm going to answer. So now in ringing, the oxygen, as usual, it will come and take away this. Okay? This OH, this H, and then this, the H, it will donate its electrons to this carbon. Okay? As you can see from here. The H is going to be taken up by the O. And you seeing the blue H on O? And then finally, the charge that remains on this O is going to be donated to the carbon, so that you end up forming a ring structure. Are you seeing the ring structure? And so in this ring structure, this is going to be our carbon 1, this one, and then this will be our carbon 2, this one, carbon 3, 4, 5. Now are you seeing this carbon 5? This carbon 5, because it is the one whose oxygen is going to donate the electrons here to form a ring. Now, are you seeing this carbon 6, that it remains outside hanging? Yes, so it is this carbon 6 with its alcohol that becomes like a group that is attached on the overall ring. Have I answered?
Over.
Oh, wow. So, what else is bothering you?
We'll proceed.
We proceed, eh? So the overall structure is going to be this, with a glucose, okay, then O, and then carbon here with OH down, then carbon here with OH down, carbon here with OH up, carbon here with OH down, and then carbon and CH2OH. So this is glucose. Now for maltose, the difference is on carbon number 2, whereby, did I say for maltose? For galactose, the difference is on carbon number 2, whereby the OH now is inside and the H is down. but you get all these details when you dig deep. That's where the difference is. Okay, yes. So let's see how condensation is going to take place. As usual. So if you have your glucose, okay, and this is my glucose, I'm trying to sketch, and this is carbon, this is carbon, this is carbon, this is carbon, and this is my CH3OH. So I'll indicate the OHs that are going to be useful here. So you have the H here, and you have the H here, the OH, and then the same applies. You have the OH, and you have the H here. So now this is one glucose molecule. Okay, so this is one glucose molecule. Now the glucose molecule is going to condense with another glucose molecule. So let's put another glucose molecule. Maybe let me put the H here, and then O. I'm trying to draw just this. So this is carbon, then this is it, then this is the H. Now the H's cannot condense, and then this is it, this is the O, this is carbon 1, this is carbon 2, carbon 3, carbon 4. So I've just drawn another glucose molecule. Okay, so I've just drawn this. So with condensation, this OH, this, oxygen has lone pairs, so it will donate the lone pairs of electrons to the H, to the neighboring H, so that, oh, this is not what I want. I want a pen. So that the H now comes and the oxygen takes away this H together with this own H, then they combine to form water. Okay, now because water is lost, then this is a condensation reaction. And so when water is lost, what is formed? We shall form this. So let me just use rings. So you have the CH3OH here. You have the OH here, and you have the H. Similarly, you have the H here, but now the OH, remember, it has gone for 1, and it has gone with one hydrogen. So we shall remain with O, and the O is the one that is linking one glucose molecule to another glucose molecule. Something of this kind. And you have OH this side and H here, then you have an alcohol here. Now it is CH2OH. Even this side it's CH2OH. So this, the whole of this, it's a disaccharide. Okay, and since the disaccharide is formed from glucose to glucose, then this is maltose. Okay, and this bond here, this one, this bond, it is our, the bond is our 1,4. Why 1,4? Because it is formed from carbon 1 and carbon 4. So it is 1,4 glycosidic bond.
Teacher, 1,4 coming from where?
From this carbon 1, okay, and the carbon 1 is combining with carbon 4.
But if, Teacher, for me, if I count, I'm seeing carbon I'm not seeing carbon 4.
You're not seeing carbon 4?
Yeah.
Okay, let's count from here. This is 1. Not so? This
Teacher,
is
yet we are.
okay. Okay, let's count from here. It is the same thing. This is the same thing, but because this one is bigger than this, that's why we are
Let's
counting
use
from
the
here.
other. Let's use the yellow one.
We use this one, eh? It's okay. So this is going to be, let me use a different pen, in this case, this one. So this is at each corner is a carbon atom. I hope you remember that from organic chemistry. Okay?
Yes.
Good. So at each corner is a carbon atom. So we have carbon here, and this is carbon 1. This is carbon 2.
Teacher, I thought where the functional group is where the, and I thought that
Mm.
that CH is
This
it
one, eh?
CH? Yes.
Mm.
So I thought we were supposed to start from the
No,
next
no,
carbon.
no. This one is carbon 6. This is, okay. From organic chemistry. Okay, no, that's not the case. So while you're concerned, now I get you. If you have this, maybe cyclohexene, hexane. Okay, now I get your concern. And you have your CH3OH. Okay? So where the CH3OH here, that becomes carbon 1. So this is your concern. Now, that's the case if they are all carbon atoms. Okay? If the ring is made up of all carbon atoms. Because see, this is carbon, this is carbon, this is carbon, 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 and carbon. But you see, our ring, it is a heterocyclic compound, whereby in the ring, you have there oxygen. Okay? You have there oxygen. So our carbon 1, okay, in our in our chain structure, straight chain, in our linear structure, is retained as carbon 1. Not so? Yes. So that this one becomes 1, 2, and then this one is 3, and then this one is 4, and then this one is 5, and finally 6. Even in this will be 1, this will be 2, this will be 3, this will be 4, and then this one will be 5, and finally 6. So the link is between,
Teacher,
yes.
you can't say.
Mm,
Why did you start from for this last glucose?
mm.
Why did you start from that corner where I said carbon? Why no.
It is the same. It is the same glucose. It's the same. You see, it is the same. I'm combining this
No, what reason did you give to start from there?
from here, not here, right?
From where you have started from to get like that one for
1 glycosidic bond. So the reason is simple. It's because in our linear structure, you remember our linear structure, the carbon 1 was this CH. So this one is carbon, this one is carbon, and so on. So this was our carbon
yeah.
1. So because our compound is a heterocyclic compound, you have oxygen within the cyclic compound, then we retain our carbon 1 to be our carbon 1. So this is going to be our carbon 1, then 2, 3, 4, 5. Okay? And then 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6, and so on. Does it make sense now?
No.
It doesn't, eh? Maybe. What is still the naming is still confusing. Maybe we can, but I don't want to postpone anything to after the lesson. You still ask.
I'm not saying that is that's why you have started from where like for this first glucose I've seen, but for the other glucose no.
Okay, what is the reason for the first glucose?
For this first glucose, it's where the oxygen is. I guess where the oxygen and the
Which
hydrogen
oxygen?
are.
This oxygen, eh?
Yeah.
Hmm.
Then for this other one, even now you're starting from like there is nothing.
Oh, I get you now. So know that there is nothing. There's supposed to be OH, there's supposed to be this. But because my screen, I can't write anything beyond this. Okay? And because I wanted, it's a must, I wanted to illustrate, then it's because it's the reason why I didn't write the OH and this H. Does it make sense now?
Yeah.
Yeah. Good you've asked. Good you've asked. Yeah, so that's amazing. Thanks for the asking. So that is the advantage of a lesson over just a video. You ask until when you get to understand. So the nomenclature, it still remains the same, okay? So this is, and it is still the same glucose, same glucose, same glucose, same glucose, okay? So the nomenclature remains the same. This has carbon 1, this has carbon 2, this has carbon 3, carbon 4, carbon 5, and then this one has carbon number 6. Okay? Yes. The same applies to this carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon number 6. So therefore, if this carbon here condenses with this carbon, then the bond that is going to be formed is 1, 4, because it's between carbon 1 and carbon 4. Hyphen glycosidic bond. So I hope it's now okay. We can proceed. So even with other disaccharides, it is the same concept. Even with polysaccharides, if you want to form starch, now you further condense these, you further add glucose molecules here. Very many of them, same reaction. And the bond that is going to be formed, it's a glycosidic bond. If you are forming cellulose, same reaction. We are going to see the difference between starch and cellulose. But it is same reaction. Okay? Same reaction. Condensation. Okay? Forming glycogen, in other words, as if you understand this concept, then you'll be good to go. Now I'm going to erase everything that is on the screen. So I hope now disaccharides are ready. Okay. Now with the chemical tests, like we said, all of them, all the three, the two are non-reducing sugars, and one is a reducing sugar. And which one is a reducing sugar? Maltose. So maltose is when you carry out a test using Benedictine solution, then the Benedictine solution will change. Okay? From a green solution to a yellow solution to a yellow PPT, then to an orange PPT, and finally to a brown PPT. But for these ones that are non-reducing sugars, then we have to first boil them in HCl. Now boiling in HCl, it will hydrolyze them, okay, into monosaccharides. For instance, if it is sucrose and you boil sucrose in HCl, then it will undergo hydrolysis to give you glucose and the fructose. And we say that all these ones, they are all monosaccharides and they are all reducing sugars. So when you come and then add the Benedictine solution, okay, then you obviously get the positive tests, positive results because of the glucose and because of the fructose. But before you add Benedicts, when you added the HCl, the solution became acidic, and such an acidic solution is not good for Benedictine solution to work. So as a result, then we shall add sodium hydroxide. What is it for? To neutralize the acid, so that you provide that condition. You provide that condition for Benedictine solution to work. Not so? Yes. Any queries before we move to another slide?
So what's the purpose of sodium hydroxide?
The sodium hydroxide, it's for neutralizing the acid, because remember you add acid and then boil. So the acid,
Then what?
then
The acid is the hydrochloric acid.
yes, HCl,
So if
hydrochloric.
you add HCl, you would have acidified the solution.
Yeah, the solution would have turned acidic, which is not good for the Benedictine solution. It cannot work in acidic medium. Okay? So we add there sodium hydroxide to neutralize the acid that has been added, so that the pH of the solution is restored, becomes slight alkaline for the Benedictine solution to work. So that when you boil it, then you will see color changes. Not so? Yes, I hope it is okay. So any question as far as disaccharides are concerned?
Have a look at the straight chain structure of glucose.
You want to have a look at the straight chain structure of glucose. Okay, let me take you there. Yeah, it's here. Oh, you just wanted to see, eh? It's okay. It's okay. Okay, it's okay. So let's talk about the polysaccharides. Now from just, okay, let's not take things. So poly means many, and then saccharide means sugar. So in simple terms, you can call it many sugar or many sugars. So these are carbohydrates that are made up of very many sugar units, okay, that are in a repetitive condensation reaction, okay? It's just a repetitive chain. They do condense together to form a carbohydrate with very many sugars, a long chain of carbohydrate with many sugar units. So it's as simple as that. And we have different examples. Number one, you've ever heard of starch? Okay? And this one is a polymer. It's a polysaccharide. Okay? You've ever heard of, for instance, cellulose? Okay? It's a disaccharide. It's a polysaccharide. You've heard of glycogen? It is also a polysaccharide. And all these polysaccharides, they have different functions. They are found in different organisms. I hope you know that. Where do you find starch? And what is it for? Where do you find cellulose? And what is it for? Where do you find glycogen? And what is it for? So they are found in different locations, and they perform different functions. And so as a result, they possess features, okay? Different features that make them perform their own functions. So before that, let's talk about the properties. Number one, they are not sweet. This is obvious. If you eat a raw mango, and a ripe one, which mango is sweeter? Now obviously all of you are saying ripe. So why is a ripe mango sweeter than a raw one? It is because a raw one has more of starch, and starch is a polysaccharide. But during the process of ripening, then starch undergoes hydrolysis to produce more of glucose and maltose. For example, in grapes and maltose and other ripe fruits. So now the ripe mango is going to be sweet, and the raw mango is going to be that sour. Think of maize flour, think of wheat flour. If you try to test those two flours, do they have any sweet taste? Or they are just, yes. But when you find ways of hydrolyzing them, okay, into their monosaccharides, then they will become sweet. So they are not sweet. Two, they don't dissolve in water. Yes, they don't. Get wheat flour and dissolve and put it in water, okay, and see if you are going to form a clear solution, a colorless solution. Get the cassava flour. Get that is pure starch, and you dissolve it in water and see if it will dissolve. Number two, are they crystals? Obviously they are not. It's a powder. Get cassava flour. It's a powder, isn't it? Yes. Then high molecular mass, of course, because they are made up of very many monomers, and they are non-reducing sugars. You don't expect them to change the color of Benedict's solution. Not so? Yes. So let's talk about the examples. We have starch, we have cellulose, we have glycogen. Now, these ones, they are conjugated. Let me say conjugated carbohydrates, whereby these ones, they are 100% carbohydrates. 100% carbohydrates. But these ones, they are carbohydrates, but carbohydrates with other non-carbohydrate groups. Okay, maybe inulin. This one is a polymer of fructose. But talk about chitin, talk about mucopolysaccharides, mucin, talk about lignin, and we are going to study the structures of each. Okay, where we shall be able to tell. Talk about hemicellulose. Okay, it is also supposed to be there. Hemicellulose. So on top of being a carbohydrate, you have other groups. Okay, yes, you have other groups that are attached on the overall ring, on the overall chain. Okay, yes. So let's see. Let's talk about starch. I think it's what should come next. Let's talk about starch and cellulose. They are the ones that will give us a clear hint, a clear view of what we are talking about, of what a polysaccharide is. So now, starch is a polymer that is formed by condensation of alpha glucose molecules. Now I'm introducing another term, alpha glucose molecule. Okay? So before we go far, you need to understand the basic structure of glucose. And then after understanding the basic structure of glucose, then you understand alpha and beta glucose molecules. Okay? Beta glucose molecules. Now with alpha glucose, the difference is on carbon number 1. They are all the same, but the difference is on carbon number 1. Anita, you still remember the carbon number 1? Okay, so now, so with carbon number 1, let's draw our basic structure of glucose. So we have O here, we have our carbon 1, then we have our carbon 2, then we have our carbon 3, then we have our carbon 4, our carbon 5, and finally our carbon 6. So this one, it's an ethanol. This is COH. Okay, then now this is O, this is H, this is OH, then this is H, then this one is H. They do alternate. Then this is OH, then this is H, then this is OH. Hey, this is OH, sorry, and then this is H, and finally H. So now this is our basic structure of glucose. Now I've not drawn this for a reason. Now in alpha glucose, the OH here is oriented downwards, and the H is oriented upwards. Now this one is an alpha glucose molecule. But in beta glucose, maybe let me also sketch something here. Let me take this one here to create some space. So this is our glucose. This is carbon number 6. This is oxygen. This is carbon number 1, carbon number 2, carbon number 3, carbon number 4, and carbon number 5. And finally, carbon number 6, and this 6 has an alcohol. Okay, then you have let me first leave this for a moment, and then you have the OH here, and then you have the H. Now the sides must all be equal. OH, the OH do alternate. You have the OH here, and you have the H, and finally H. Now in beta glucose, the OH is oriented upwards on carbon number 1, and the H is oriented downwards. That is just the difference. Let it sink. That is just the difference. And you may look at that difference as minor, but hey, it's not minor. It's not minor. Okay? this difference creates a big impact. Okay, and this one is beta. So in beta glucose, the OH on carbon 1 is oriented upwards. Okay, and in alpha glucose, the OH on carbon 1 is oriented downwards. I think this difference, yes, we shall see its significance. Now in starch, it's a polymer that is formed from condensation of alpha glucose molecules, these ones. Okay, and when these alpha glucose molecules condense, they form what we call an alpha 1,4 glycosidic bond. Is that okay? And now it is this alpha 1,4 glycosidic bond that is now going to hold the glucose molecules close together in starch. Okay, and we are going to see, we are going to draw. Okay, now the starch is highly coiled into a helix. I'm going to show you how it is highly coiled when we talk about condensation. And it has two components, the amylose, and this one stays blue with iodine, and amylopectin, which stains red to purple. But the whole of it, starch is made up of amylopectin and amylose. So that's why starch, it stains dark brown. Okay, the whole of it. That's why starch is going to stain dark brown. But now think about the functions of starch. You know it's a storage compound. You know that? Yes, I also do. And so imagine if a storage compound was just you form the parallel chains. How much cell would you need to store enough starch to feed you for a week if you are a plant? Obviously you need too much. So to increase on the storage capacity of starch, to reduce the packing space so that little space packs enough, then the starch should be highly coiled. And the coiling the starch, the high the starch that you will be able to store. Now imagine such, okay, a coiled substance and such a linear substance. Which one are you going to easily store in your cell? Obviously, it is this. And what brings about the coiling? It is the structure of the glucose. We have seen that starch is made from alpha glucose molecules. So during condensation, let's talk about condensation and see. During condensation, I have it here. During condensation, different alpha glucose molecules, they will condense with each other. You can see this is one glucose and the OH is down. It will condense with a neighbor where the OH is down. Okay, maybe let me get some.
Teacher,
Yes,
as for them, they don't have the OH with the hydrogen. I'm only seeing OH, OH.
where? Here down, eh?
Like all of them, they're having only OH and HO. They're not having OH and with hydrogen.
You mean to put hydrogen here and here, right?
Yes.
Oh, good. That's a good question. This is just a condensed structure, okay, where the hydrogens were not shown. Still, I will take you back to organic chemistry. If I draw this C, 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 what is this? I hope no naming won't be. So if I draw this, I'll put hydrogen here and another hydrogen here, hydrogen here, hydrogen here. So it is time consuming. I hope you can see. So this is our cyclobutane. Let me name it for you. So writing this, yes, this is cyclobutane and all of us can see, but it's the same as writing this. Okay, it is the same as writing this. So this is still cyclobutane. If there is a group somewhere, then I'll put the OH here, and I also put, that is if it has two groups, okay, and then you put the OH there if it is there. So it is the same way. So even this side, we just put the OH because they are the groups, okay, that are needed. But the H's, the hydrogens, are there. Is it okay now? Yes. So you can see the focus, let the focus be on carbon 1 and carbon 4, because that's where the science is. Okay, that's where the science is. So on carbon 1 in alpha glucose, okay, if maybe the alpha glucose is going to be this, let me first sketch it so that you don't ask me where is the OH coming from. Sorry, this is carbon, okay, this is carbon 4, and then carbon 6. So you have the OH here and you have the OH here. So even with another one, if you get another this and you put it aside, you will have the OH here, okay, and then carbon 4, then this is then this is carbon, 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 and then oxygen, yeah, the same OH. So you can see, maybe let me get some pen. So in alpha glucose, this is alpha glucose and this one is also another alpha glucose. So because among all, the OH on carbon 1 and the OH on carbon 4, I mean this carbon and this carbon, all the OHs are oriented on the same side. Are you able to see that? When they come close to each other, all the OH, they are oriented on the same side. So they will easily condense together to form this bond. Even when you bring another one, still they will be oriented on the same side. Still they will combine to form same bond, 1,4 alpha 1,4 glycosidic bond. So even when you bring another one, the same thing. Are you able to see that? Same thing, same thing, same thing, same thing, same thing. Are you able to see that? Somebody say yes. Then I tell you what next.
On this first structure, why is the OH has OH and on the second one it is H coming first?
Which structure?
Where are they joining from?
Here.
Why? Yeah. Why is it for the other structure? Why is it the H coming first, then followed by the O?
Hey, you mean here? Okay.
Yeah.
Okay. So whether you write this, okay, whether you write this, it still remains the same thing. Not so? Yeah, order doesn't matter here. Okay? Yeah, that was some good question. So whether you write this, the order doesn't matter. I just wanted to see how I can illustrate. I take away this H and then I form the water. So is that okay? Because what I'm going to communicate next requires a clear understanding of this.
Excuse me, sir.
Yes.
Why does there remain oxygen only?
Why does it remain oxygen only? Yes, because you see, one, it is OH. It is OH from one glucose molecule and another OH from another glucose molecule. So when this one, oxygen, now I don't want to go more in chemistry, but the oxygen of one glucose molecule is going to come and take away the oxygen of the hydrogen of another glucose molecule, so that they two form water molecule. The two form a water molecule. Okay? So you can see if you do this and you form water, then this oxygen is going to remain. Okay? And form a glycosidic bond. So basically it is simple. So that's why you're seeing oxygen here, and oxygen there. So I hope that one is okay, because I can speak the next. I can say what is next. Okay. Now let me first clean before the next. Now the next, I want you to observe this. Are you saying that these groups, they will be oriented outwards? Are you saying that these groups, they are oriented outwards among all? Okay? This OH group. Are you saying that they are oriented outwards? Yeah, that's good. So now, when you get two strands, okay, of for instance starch, okay, now because these groups are oriented on the same side, okay, the OH groups, these ones, because they are oriented on the same side, and by the way, they are also oriented inwards. Okay? Then these OH groups can form cross linkages with each other. Like you have this OH group. Okay? Have we started bonding in organic chemistry? No. In inorganic? No. So we shall study it. So these OH groups, they will form cross linkages within each other. So you have the OH here and another OH here. So they will form cross linkages. In other words, they will attract each other. This one will attract this, and also this one will attract this, and also this one will attract this. So they will form forces of attraction amongst themselves. Okay? So now these forces of attraction that are formed amongst themselves, okay, they will be able to pull the structure of starch, okay, to bend. Because when it's like pulling here, also pulling here, and also pulling here. So the structure of starch to end up bending. And so the more the cross linkages, the more the coiling. So the structure of starch will end up coiling. Okay? And you form such a coiled structure. Is that okay? Why is it coiling? Because all the OH groups, they are oriented inwards, and so the coiling, they will end up coiling, okay, to make the structure of starch to be highly coiled. But now let's see for cellulose. How does the structure of starch? Maybe before adaptations, let's first talk about the structure. Okay, glycogen is fine. Let's first talk about the structure of cellulose before we talk about the adaptations. Now for cellulose, for it is going to be formed from beta glucose molecule, or beta glucose molecules, very many. And we say that the difference with beta glucose is 1. The OH on carbon number 1. This is O, and this is another carbon. Okay? So the OH on carbon number 1, it is oriented upwards. Okay? And the OH and the H is oriented downwards. So as a result, when you are forming the cellulose molecules, cellulose strands, cellulose fibers, it will be kind of different from how starch is formed. And so basing on that difference, then you have parallel chains of cellulose. And hence the two perform different structures, where this one is used in cell walls and starch storage. Let's see. That's what I'm talking about. So this is basically what I'm. Oh. So let's see how they are formed. Now, are you seeing this glucose? OH, OH, it's normal glucose. But the difference is, okay, the OH is oriented upwards. Okay? And it is the OH which condenses. Are you seeing? Now, let me illustrate it here. You know, when you don't draw, certain things become hard when they are supposed to be easy. So this is my glucose, C, 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 and then C, and then C. So this is CH2OH. And then this one is OH, and then this one is H. They do alternate, OH, and then H, now OH, and then H, and finally H. Now on carbon number 1, since it's beta glucose, the OH is above and the H is down. So now this beta glucose molecule is going to condense with another beta glucose molecule. Now in another beta glucose, the OH is down. Are you seeing? The OH is down. So the OH, if you bring it here, the OH is going to be down. Yet on carbon 1, the OH is up. So there is no way they can condense. Okay? Because they have different orientations of the OH groups. So because of that, what happens? The second beta glucose molecule is going to somersault. Okay, it is going to rotate 180 degrees Celsius. So I usually say you quote it as somersaulting. You know, when we were young, we used to beat summers, and you even walk with arms. Okay, so that is somersaulting. So it will somersault, okay, and this OH will go up, and the OH which was oriented upwards, it will go down, as you can see, so that it's now able to condense with the OH that is up. Otherwise, if it wasn't the case, then it wouldn't. You can see the group that was up, it is now down. You can see the OH that was up, that was down, it's now up. Okay, so that they are able to condense. Then after you've condensed, you've formed two. To add another one, for it will just add, because now the OH will be down, it will just add. But now to add the fourth, it will also somersault. Are you seeing? Are you seeing the OH? The CH, it is down. The alcohol is down. So now, because of that, it will form a strand with alternating groups. The group is up, then next time it's down, next is up, next is down, next will be up, next will be down. The OH is going to be down, then in the next glucose molecule it's up, the next it's down, in the next it's up, and so on. So as a result, when the strands of cellulose lie together in a horizontal plane, like how you can see this, then these alternating groups, they will form cross linkages, hydrogen bonds, with other strands of cellulose. Now, instead of coiling, then you maintain that parallel sheet, parallel structure of cellulose. But what makes that? It is because of beta glucose molecule with the OH group that is oriented upwards. So the somersaulting, that rotation of 180, it is the one that brings about the different orientations, the alternating orientation of these groups. And so they will be able to form the cross linkages with other chains of cellulose fibers. But for starch, the chains that are formed, they are internal. The cross linkages that are formed, they will be formed internal. Okay? Which will end up forming that coiled structure of starch. So, any queries? Now, if there are no questions, we are going to stop from here. Now, from the quick insight that I've given you as far as starch and cellulose are concerned, you go and compare the structures of starch, do some reading, and try to compare the structure of starch and the structure of cellulose, and see how the two structures are different from each other, how they are similar to each other, and how the two structures really suit to perform their functions. If you can do that, trust me, then this topic is going to be so easy for you. So go and do some reading. Okay? In our next lesson, or in our next video, then we shall be able to see we shall be able to relate, and then we look at other carbohydrate, other polysaccharides, and how those other polysaccharides are relate to their function. Have a nice time.